Great. So our next speaker is Misha Gekhtman from Notre Dame, speaking on generalized cluster structures and periodic difference operators.
Right. Thank you. So thank you for the invitation, for organizing this event. My apologies that after seeing so many beautiful slides, you will have to now see real handwriting, but maybe it's at some point people will go back to using blackboards, and then, well, someone has to use handwriting, so you're not completely, unlearn this. So this talk is based on joint finished work with Misha Shapiro and Alec Weinstein, and also on some ongoing work with Chris Fraser and Trey Trample. And what I'll try to do is to convince you that this word generalized is actually warranted, that this is not just something that people invent because they can generalize in existing structure, but something that comes naturally in geometry and then hopefully in physics. So last afternoon, we saw several applications of cluster structures in theoretical physics, and maybe what I'm about to describe is going to be was going to be useful as well. All right, so I see that for some reason my broadcasting stops. Just a second. Sorry, I'm going to reconnect, but let me just say that there is there are several players in what I'm about to describe, and one is a very classical object that is the space of periodic difference operators, or finite band periodic matrices. With three diagonals, they're known as Jacobi matrices, and they are related to many classical subjects such as orthogonal polynomials, spectral theory, and various integrable systems, including periodic total lattice and discrete KP-IRs. And if we're talking about integrable systems, they usually have underlying Poisson structures. So another players that we will see will be Poisson varieties on which there is a natural group action, in particular Poisson Lie groups and their Poisson homogeneous spaces. Again, those are prominently featured in theory of integrable systems, in representation theory, in quantum groups, and so on and so forth. And finally, probably the most recent player is cluster algebras that were discovered by Fomin and Zelevinsky about 20 years ago. They were motivated by questions in representation theory and a story about dual canonical bases, but quickly became tied with questions in combinatorics and representation of algebras and high-tech Müller theory due to work of Fock and Goncharov. And for us, for my collaborators and myself, was Poisson geometry. So maybe I will review the general philosophy of how you look for cluster structures and Poisson varieties, and then I will at least sketch a definition of a cluster structure. The full definition usually just bores everybody, so I'll just do examples instead. Our setup will be as follows. We have a Poisson variety on which usually there is a natural toric action. And what we want to do is construct a nice family of coordinate charts, which we'll call clusters on this variety, with the following properties. First of all, we want every coordinate in every chart to be a regular function. So let's suppose V is a set of GLN, and then I want something polynomial in matrix entries. I want these functions to be homogeneous with respect to the toric action. And I also want this to be almost canonical in a sense that Poisson bracket is very simple between any two of such functions. The bracket is just their product times some integer constant. This is what became known as log canonical Poisson bracket. Next condition, very strong condition, is that any two such charts are connected via Laurent polynomial transformations. That means in particular that inverse of every such transformation is expected to be a Laurent polynomial transformation. And finally, we want every regular function to be expressible as Laurent polynomial in terms of every one of these coordinate charts. Right, so it's a lot of requirements. It's not clear that you have any such examples, but in fact you do. So let's consider the simplest possible example. In this case, our variety is GL2 equipped with standard Poisson-Lie bracket. So let me remind you that Poisson-Lie bracket is a bracket on a Lie group that respects multiplication. In other words, multiplication map is a Poisson map. So we just consider the usual coordinatization of GL2, and I can write in this case this Poisson-Lie bracket explicitly, and it almost entirely log canonical. So all these brackets look exactly like we wanted them to look, except for one. So the bracket of A and D is twice B times C, so it's not log canonical. And then we have a Casimir, which is a determinant. Right, so this fact that the bracket in natural coordinates is not log canonical can be easily remedied. In fact, we can find two clusters that satisfy all of the properties that we want. One is A, B, C and the determinant, which is a Casimir, and another one, D, B, C and the determinant. And those two are related by a very simple transformation, otherwise known as a formula for 2x2 determinant, right? But we're going to decorate this formula with additional structure. So in case I forgot how to compute 2x2 determinant, this picture here, which we will soon call the quiver, tells me how to do this. So I know that the product of A times D should be a product of two variables from which arrows point to the variables that I'm going to transform, plus the product of all the variables to each arrow points from these variables that I'm going to transform. So this is called a quiver. We have our variables attached to vertices of the quiver. And this transition from A to D is called a cluster mutation. And I did something to the quiver too. I just reversed all the arrows, but this operations will be a little bit more involved when we go to more complicated examples. So this is an example of the situations that we want, and let's just review all the ingredients that we really need. So on the Poisson side, again, we have this variety with a toric action and Poisson bracket, and this nice coordinate system in which actually from now on I will postulate that some of the variables I'm not going to be allowed to transform. Those are called frozen. There are Poisson geometric reasons for that, but maybe I'll talk about this later. And so suppose I'm lucky enough to find one such nice coordinate chart. Then on the cluster side, I will call the same coordinate chart an initial seed. Variables in it I will call cluster variables. And there is a quiver here connected to this. How can I find it? So quiver is a directed graph. It has an adjacency matrix. And to find this adjacency matrix, I can relate it to my Poisson bracket through the following relation. So the adjacency matrix of this quiver times, so I'll just take part of it, right? So notice that this one is rectangular because I do not consider any arrows between vertices corresponding to frozen variables. So this is a relation between them. So it's this partial inverse, right? And nothing very complicated. So I claim that once you have such a situation, you can build a cluster structure, meaning that you can build another set of coordinates with nice Poisson relations through the following exchange relation. So you take your old coordinate set, you throw away one particular variable and replace it with another. And this new variable is related to the old one through these relations that we saw on the previous very simple example. old variable times new variable is sum of two monomials. One monomial is determined by arrow pointing to the vertex at which we make this transformation, and another by arrows pointing from that vertex. And remarkably, as a result, you'll still get a coordinate chart with a nice Poisson relations, and the same relation between the Poisson bracket, or the structure constant of Poisson bracket, and adjacency matrix of the quiver. That is, if you do something to the quiver as well. And that's something is called quiver mutation. Because originally, this was not defined in a different way. Fomin and Zelevinsky defined matrix mutation, then translated into quiver mutation. And our motivation, one of our motivations long time ago, was to understand this quiver mutation. And then we realized that it is nothing else other than just a change of coordinate for a Poisson structure. All right, so what is this quiver mutation? I will explain in a second, but we wanted some additional condition, right? Because we wanted all the functions to stay regular, and for that, there are usually reasons for that. And we wanted this completeness property that every regular function is a Laurent polynomial in terms of any of our coordinate charts or clusters. And in the language of cluster algebras, it says that the ring of regular function is naturalized isomorphic to so-called upper cluster algebra, but I don't want to go into details on that. So completeness is something that follows from the geometry. It cannot be obtained from just pure cluster algebraic considerations. And what is a quiver mutation? So I will remind you this or explain this by example. So if I transform variable number k, so I'm mutating at vertex number k, what I do, if there is any directed path, short directed path through the k, I draw a shortcut. Then I reverse all the arrows which are incident to k. So there is shortcut here. There should be also shortcut here and shortcut here. And then in my quiver, I'm not allowed to have loops or two cycles. So whenever I create through the process that I just described a two cycle, I'll just remove it. And so as a result, this is a summary quiver mutation. All right. So this structure turned out to be remarkably useful, and I'll just mention a couple of examples which may be closer to physics. For example, if there is a sequence of mutations that preserves both the quiver and cluster variables, so we mutated many times and obtained the same quiver, the same cluster variables up to permutation, each such situation leads to an identity for the Rogers logarithm function, and this includes in particular famous Zamolodchikov conjecture that was proved by Fomin and Zelevinsky, and this theory was extended by many people, including Tomoki Nakanishi, Bernard Keller, and many others. Suppose now that we have a sequence of mutations that preserves only the quiver. And to this, you can relate discrete dynamical systems that preserves a symplectic structure, because, as I said, quiver encodes the Poisson structure. And so if you have a sequence of mutations that results in the same quiver, but different functions, so functions that we will obtain will be birationally related to original one. So you can view this as a discrete map that preserves symplectic structure. And under other additional condition, you can show that this will give you a discrete integrable system, in particular, if your quiver can be drawn on a torus, for example. Okay, so let's consider another example. So this is so-called cluster algebra of finite type an-1. For finite type means that you mutate however many times you want, but you will only get finitely many different, essentially different functions, right? And classification of such cluster algebras is parallel to Cartan-Killing classification of finite type Lie algebras. This is another theorem of Fomin and Zelevinsky. And so Young and Zelevinsky realize this type of cluster algebra. One of many realization is using tridiagonal matrices, just finite tridiagonal matrices viewed as a subset in the group. In fact, they form a so-called double Breuer cell in the group, intersection of two specifically selected opposite Breuer cells, but that's not that important for us at the moment. So, we have this set of tridiagonal matrices. It is actually a Poisson submanifold with respect to a Poisson-Lie bracket on the group. This is in particular where finite Toda lattice lives on this submanifold. And you can find this initial nice set of coordinates using the following, just matrix theoretic concept. So you have a matrix, just consider principal minors emanating from the lower right corner. So you'll have all these minors lifted here, and then as frozen variables, you take the determinant and all the off diagonals entries, and then the claim is that these minors will form this log canonical coordinate system with respect to Poisson-Lie bracket. And then if, according to technologies that I just described, you compute the quiver will look very simple. And the cluster transformations, even though they involve division, will not throw you away from the set of polynomial functions due to Dinano, Jacobi, Dodgson, Short-Lucke relation, whatever is your favorite. And moreover, every cluster variable in this situation can be described as a particular row and column dense minor, symmetric minor of this matrix. So this is the theorem of Young and Zelevinsky. So you have just finitely many of them, and you can describe them conveniently using matrices. Well, okay, so let's consider one more example. And this time we go from this Poisson-Lie group G, in this case G is GLN, into its so-called Drinfeld double. So there is a well-known procedure how to make the Drinfeld double, which as I said is just direct product of GLN by itself, how to make it into a Poisson-Lie group. This endows the double with a quadratic Poisson bracket in terms of pairs of matrices that live in the double. And let's say n is equal to 2. So this Poisson bracket is quadratic. It's quite complicated, but you can still find this log canonical set of coordinates in more than one way. So I described just one of these examples. Some of them will have to be frozen in this case. And then I select 3 more coordinates. I claim they're all log canonical. I compute my quiver according to procedure described previously. And then I will run into the following problem. If I try to do this cluster transformation according to the rule I described before at this vertex, the result is no longer a polynomial, right? So you can easily check that this is no longer a polynomial. So we have the technology, but it breaks somehow at this point. So can you fix it? It turns out that you can if you allow yourself a more complicated cluster transformations. Namely, you replace this cluster relation of the form product of all the nu is equal to the sum of 2 monomials with a longer relation. So in this case, it will be sum of 3 monomials. And all coefficients of these monomials will have a meaning in terms of Poisson brackets that we discuss. In fact, they all will be Casimirs of this bracket. And these Casimirs can be obtained just by looking at the expansion of this generalized characteristic polynomial, if you wish. Right, so this longer relation naturally appears in this case. And once you fix this particular transformation in this manner, all other properties of cluster algebras will be satisfied. All right, so this is a typical example of generalized cluster transformation. So we now allow ourselves certain control type of polynomial right-hand sides in our cluster transformation relations. And this, of course, was just an example for n equals 2, but for n arbitraries, this becomes more complicated. Relation, this generalized cluster relation now has length n plus 1. Again, the coefficients are Casimir's, and it involves some rather complicated polynomial functions on the double, which I am not going to describe explicitly. And it turns out that the fact that you can write such a relation is based on, again, on a matrix identities that we discovered, but well, I wasn't able to find it anywhere. And the quiver now looks quite complicated. But so there are, so this is for the double. Parts of this quiver are occupied by functions, which is just the minors of one of your matrices, minors of X, another one by minors of Y, another part by mixed minors, and this gray part is by something very complicated, but still regular. And you can still show that you can restore every matrix entry, every natural coordinate as a Laurent polynomial. And there is only one vertex here with this function, which I will not describe in detail because I will find its replacement soon, but this one is transformed in this generalized way. All right. So I want to point out that this picture here contains many cluster structures, not just in the double. So it contains a regular complete generalized cluster structure on the double as a whole, just usual cluster structure on GLN, which you obtain by embedding GLN diagonally into the double. And it contains also generalized cluster structure on the dual pos-only group to GLN, and then on intersection of conjugacy class in GLN with big Brouillard cell, and so on and so forth. So these restrictions can be obtained, for example, if I throw away this middle part of the quiver and then glue the remaining wings, then I will get the standard quiver for GLN, which is occupied. The initial functions are again minors, right? So in fact, it's easy to describe them. You pick a spot on the quiver, just imagine that this is an entry in your n by n matrix, drop the diagonal down until it hits the border, take these minors, and that's your cluster variable. So once again, the natural way to look for cluster variables are some, minors which are properly located in your finite matrix. So there is a quiver for dual one, but I don't think I have time to go through that. And the key ingredient here is this identity, just the matrix identities that I mentioned, which looks rather involved, but it is true for any n by n matrix. And the point here is that you can cook out this kind of relation just using just a complex matrix, using its characteristic polynomial and carefully selected polynomial functions such that you plug them inside this formula for characteristic polynomial, and it will factor into two irreducible polynomials. Right, so this will be important for us later. Okay, so that brings us to the question of how to build a formal definition of generalized cluster structure. I think I don't have too much time to do that, so we'll just concentrate on the fact that some relations are longer than others. Okay, and the rest. So you have to modify Quiver mutation. For example, if this vertex relation is of length, say d, then I will add d arrows as a shortcut, and so on and so forth. But under these definitions, all nice properties of cluster algebras remain intact. This includes Laurent phenomenon and all other properties that you would like to have. Okay, so we have this definition. Other examples, well, besides the ones that I have given to you, and in fact, there is a nice matrix theoretic constructions that gives plenty of examples. And the source of such examples is what I will call periodic staircase matrices. So just imagine that we have infinite bidiagonal matrix where, well, bidiagonals in a block sense. So we have pair of n by n matrices that just repeat along the diagonal. You can, if you wish, call it the infinite bidiagonal doublets block matrix and so on. All right, so this AB can be selected to be of special form when necessary, but it is important for us to call so-called inner diagonals in this matrix. And what does it mean? It means just if I consider diagonal and view this as a main diagonal, right? If the resulting matrix looks irreducible, then we'll call it an inner diagonal matrix. Inner diagonal. So in this example, we have two inner diagonal, which are in red, right? And suppose I want to find nice collection of minors, like in previous examples, and normally I would want to start at the bottom, for example, or at the top, and consider principal minors expanding from this point. But this matrix is periodic. There is no bottom, there is no top, so there is no base point for me, and so this can be solved in the following manner. So this is what I'm going to do. Again, let's just look at the example. I have this, in this case, 5 diagonal band periodic matrix, and in each block row, let me just cross out the first normal row, right? So this will squeeze my matrix a little bit, and what you will find out is that it will have a very well-defined, unique maximal irreducible component, which I will call phi. And in this irreducible component, now I do have lower right corner, and I can consider in this case principal minors emanating from this corner. All right, so let's give them a name. Let's call this matrix phi. Let's call this minors phi sub I. Well, so they are just numbered by the diagonal entry in this phi from which I start, and then associated with this bidiagonal matrix in a natural way is its characteristic polynomial, generalized characteristic polynomial, okay, which I can expand. And so once again, I will have this key identity. So if I take the determinant of this huge matrix phi, it turns out that I can transform it into another even larger polynomial using my coefficients of characteristic polynomial. So it has all, and some other of these functions phi. So it has all the features of the generalized cluster transformation, right? It looks like that. And so naturally one asks if there is a corresponding cluster structure where this plays a role of generalized transformations. The answer is yes. And again, periodic band matrices give such an example. And there are all the ingredients that we discussed before. There is a Poisson bracket, there are cluster transformations, and so on. So in this case, so I'm considering periodic k+1 diagonal band matrices. I'm going to freeze. I'm never going to transform this entries of the leftmost and rightmost diagonals. And if I perform this excision of rows, I will obtain the maximal reducible component of this size. Okay, and this will be the number of functions that I will get as minors of this phi. And what is a Poisson bracket? Okay, so I can rewrite this elements of this band matrices in terms just of a single row, block row, as linear matrix polynomials. And it turns out that these linear matrix polynomials, they form a Poisson submanifold in the set of all matrix polynomial with respect to the famous trigonometric R matrix bracket, which I will just write down here. It's associated with this so-called trigonometric solution of a classical Young-Baxter equation. And this, what used to be called Leningrad, and now it's called St. Petersburg formula, it records all the Poisson brackets between the entries. So this is a famous structure in integrable systems, and my band matrices form a Poisson submanifold with respect to this. And then we can state the following theorems, that this family of functions that I constructed, together with a quiver, which just can be computed from the Poisson bracket as before, defines a regular, complete, generalized cluster structure compatible with the Poisson bracket above. So there is only one generalized transformation right here, and the rest of these functions are transformed in the usual way. All right, I think I'm running out of time soon, but let me just let's just compare this with a Young-Zelevinsky example when we dealt with, let's consider tri-diagonal case. So in finite tri-diagonal case, we mentioned Young-Zelevinsky theorems saying that they realize finite type cluster algebra of type an-1, and all the cluster variables can be then associated with minors of this tri-diagonal matrix. So this is a theorem. Let me remind you again. But in our case, something cuts off, so I'll just say it. So in the periodic case, we have an analog of that, namely in this case. So let me just show you the quiver. In this case, we're talking about infinite periodic tri-diagonal matrices, but we still have finitely many functions in our initial seed. One of them transforms in this generalized way, and this will become a finite type but generalized cluster algebra, but now of type Cn, and again all the cluster variables which are in one-to-one correspondence with positive roots of Cn will be again dense minors, but now we can shift along the period of this matrix. All right, so I'm pretty much out of time, so let me just make a few remarks. As often happens in a series of cluster algebras, if you find cluster structure in some geometric object, the same cluster structure can be then realized, can have different geometric or algebraic interpretations. So in particular, this generalized cluster structure associated with tri-diagonal periodic matrices, the same structure appeared in a study of monoidal categorification of representations of quantized universal envelopment of the loop algebra of SL2, right? And this was done by Anne-Marie Gleitz, and it was conjectured that similar result holds for UQ of SLK in general. And in a joint work with Fraser and Trample, we in fact verified that this is true, but not actually directly. So let me mention some other connections. It turned out that similar, or let me be more precise, but without giving exact definition, quasi-isomorphic cluster structure exists in a cyclically symmetric loci in Grassmannian. So we consider powers of a cyclic shift and consider a fixed point set for such power of a cyclic shift. And this has a natural generalized cluster structure, which we now have shown with Fraser and Trample is, in a sense, isomorphic to the ones that I just described. You can also find a generalized cluster structure on spaces of so-called twisted projective polygons, which are just sequences of points, so polygon will be a sequence of vectors which closes, and this almost closes, so up to a monodromy. And these spaces are phase spaces for famous pentagram maps and the generalizations. We now can describe cluster structure in space of matrix valued polynomials, which requires some extension of all the formulas, identities that I discussed before, but all of that has been done by well, replacing, you know, our simple characteristic polynomial with just determinants of matrix polynomials. We have to extend key identity. We can extend generalized cluster transformations, and that gives us more geometric examples of varieties supporting generalized cluster structures. And with this, thank you for your attention.
Thank you. Okay. Questions?
I had one very naive question, maybe
Yeah.
I can ask. So at the beginning, in the first quiver that you showed, you can read the relations from the quiver because the relations were just a sum of two monomials. Then in the generalized quivers, can you still read the relations with the coefficients? It looks
Yes,
more
exactly. Yeah, exactly. So you can still read. So if well, I was talking fast, but once again, let me just look here. So the only variables present in the relations will be those connected to this variables that being transformed. But instead of having some of these two monomials, we'll have, say, so if relation is of degree d, then you'll have, say, this variable sum over this variable in power I, this variable in power d minus I with coefficients which are attached to this. Coefficients never change. They're attached to this vertex. So only coefficients are not visible in this picture, but relation is visible. So if I were to write here d and say that this is a degree, then Quiver will contain all the information about the transformation.
Okay. Okay, thank you.